Hello and welcome to my lecture series for Control System 1. Myself, Shumon Ghosh, Assistant Professor from Electrical Engineering Department, Guru Nanak Institute of Technology, Kolkata. And this lecture series is basically for 5th semester BTech Electrical Engineering students. Now, this lecture 4 and lecture 4 we will discuss some problems or some examples on translational mechanical system, and then we will move to our rotational mechanical system. So here a quick recap. Translational mechanical system. In translational mechanical system, motion of the body takes place along a straight line, whereas in rotational mechanical system, the motion of the body takes place along a fixed axis. And in translational mechanical system, there are three basic elements, that is spring mass damper and force generated due to mass is m x double dot, where m is the mass of the body and x is the displacement of the body, and force generated due to damper, that is F is equal to B x1 dot minus x2 dot, where B is the damping coefficient and x1 is the displacement of end 1 and x2 is the displacement of end 2. Next, force generated due to spring is equal to F is equal to small k into x1 minus x2, where k is the stiffness of the spring and x1 is the displacement of end 1 of the spring and x2 is the displacement of end 2 of the spring. So this is one example which I already discussed in previous lecture, and here is the example 2. So in example 2, there is just look at the problem. There are some one spring is there, two damper is there, two mass is there, one force is applied, and for applying this force, the movement or the displacement of mass 1 is x1 and the displacement of mass 2 is x2. And in our previous lecture, we know that the number of displacement will be the number of nodes present in the mechanical circuit diagram. So here two displacement, that is x1 and x2 is present, so the number of nodes in the mechanical circuit diagram will be 2, that is x1 and x2, and there will be one reference point. There will be one reference point that is represented by ground symbol. Now just see the problem, mechanical system given in the problem. The mass m1 and m2, the mass m1 and m2 is connected through b2, that is damper 2. So, and in our previous problem, we already know that one end of mass will be connected to the reference point, that is represented by, that is one end of, we have to assume one end of mass as a fixed. So one end of mass we have to connect to the ground point. Okay, and the another end of the mass is connected to the x1. Okay, so one end of mass is connected to the ground point and one end is connected to the x1. Similarly, one end of mass m2 is connected to ground and one end of mass connected to the reference point. So, and the two masses m1 and m2 is connected through a damper that is B2. So in between M1 and M2 there will be a damper. Now M1 and M2 is connected to X1 and X2. So you have to connect the damper B2 in between X1 and X2. Okay, in mechanical circuit diagram. And this way we have to connect B1, and B1 is one end of B1 in, just look at the mechanical system. One end of B1 is connected to reference point. So one end of B1 you have to connect in mechanical circuit diagram in reference point, and one end is connected to mass M1, and the mass M1 is connected to X1. So you have to connect one end of B1 in mechanical circuit diagram to X1. Like this way you have to connect K, that is spring, and the force is connected in between x2 and mass, and that is reference point, and the direction of force will be the direction of x2. If we apply force from left to right, then the movement of the displacement of mass will be from left to right. So the direction of force will be the direction in the direction of x, that is displacement. So from that so this is very important, and if we draw if we able to draw the mechanical circuit diagram, then it will be very easier to calculate the force equations. Now here two nodes is there. Now first consider node 1, that is node x1. Now with node x1, which elements are connected? It is B1, M1, K, and B2 is connected with x1. So we have to write the force equation. So force due to mass M1 will be M1 x1 double dot. Force generated due to damper B1, that is B1 into x1 dot. Force generated due to spring, that is kx1, and force generated due to damper B2 is equal to B2, that is damping coefficient, into, here B2 is connected in between x1 and x2. So we have to take the difference, that is x1 dot minus x2 dot, that is relative velocity. So B2 into x1 dot minus x2 dot is equal to 0. So in this way we have to write the force equations. Now taking Laplace transform, now you take the Laplace transform and write down the equation after getting the Laplace transform. Now one more thing, what we have to calculate? We have to calculate the transfer function of this physical system, of this translational mechanical system. So transfer function means output by input in Laplace domain, where all initial conditions are 0. Here what is the output and what is the input? Here we apply the force, that is F. That's why the displacement x1 and x2 is occur. So here F is the input and x1 and x2 is the output. So here two output is there. So the transfer function of this problem is 2. Here is 2 transfer function, that is x1s by fs and x2s by fs. Okay, so you have to calculate x1s by fs and x2s by fs. Now for node 1 we already discussed the force equation. Now for node 2 we have to write the force equation, that is m2 x2. Now with node 2, that is x2, node x2, force m2 and a mass m2 and force f is connected. So total and damper b2 will be there. So force generated due to mass m2 will be m2 x2 double dot plus force generated due to damper b2 will be b2, that is damping coefficient, multiplied by relative velocity of the two end, that is x2 dot minus x1 dot, is equal to total force applied. So this way we can write the force equation of the with respect to node 2. Now right now we get the force equation for node 1 and node 2. Now perform the Laplace transform and then rearrange the equations, and we calculate the transfer function. Here just look at the solution. Here simple, the solution is given in simple way. You just go through, it will be easier to understand for you. Now moving to our next slide, there will be another example and very simple. Just write down the force equation, and here two displacement is there, that's why two displacement x1 and x2 is there, that's why two node will be there, and one reference point, and connect all the elements between nodes and reference point and calculate the transfer function. Very simple and very easy. And here is another one example, just go through it. And next is rotational mechanical system. In rotational mechanical system there are three basic elements, that is inertia, damper and spring. Now the inertia. Now what is a rotational mechanical system? In rotational mechanical system there will be a motion or rotation along a axis. So that is the rotational mechanical system. Now inertia, torque. So here torque will be there, and in translational mechanical system there will be a force, but here one torque will be there. So inertia torque is moment of inertia, that is capital J, into angular acceleration, is angular acceleration. So the inertia torque T is equal to J theta double dot. Theta double dot means d2 theta by dt square, where theta is the angular displacement. Next is damping torque. Damping torque is equal to damping coefficient into angular velocity. Now damping coefficient is represented by c, and angular velocity between two end is represented by theta 1 dot minus theta 2 dot, where theta is the angular displacement. Next is spring. Now spring torque will be spring coefficient into angular displacement between two ends of the spring. So T is equal to small k into theta 1 minus theta 2, where theta is the angular displacement. So here one example is there, that is simple inertia, damper and spring. So for this type of mechanical system, just write down the torque equation. That is total torque is equal to torque generated by inertia, that is J into d2 theta by dt square, plus torque generated by damper. Here friction is considered as a damping factor or a damping element. Friction is considered as a damping element. So the torque generated by damping element is b d theta dt plus torque generated by spring, that is k theta. Now taking Laplace transform, ts is equal to j s square theta s plus ps theta s plus k theta s. Now what will be the transfer function? Now what is the transfer function? Here the output, what is the output and what is the input? Here one torque is given. Here one torque is given, that's why the angular displacement is occur. So that is occurring, that is angular displacement. So here angular displacement is the output, and here we give torque as the excitation. So torque is the input. So output by input, that is theta s by ts, is equal to 1 by js square plus bs plus k. So this way we can calculate the transfer function. And here is one example. Like previous translational mechanical system, we have to calculate, or we have to draw fast the mechanical circuit diagram. Here two inertia J1 and J2 is connected through a damper, that is B1. So in between theta 1 and theta 2 there will be B1. So this way you have to calculate, or we have to write fast the torque equation for node theta 1 and then torque equation for node theta 2. Okay, then we have to calculate the transfer function. Just look at the solution. Theta 1s by ts is the first transfer function, theta 2s by ts is the second transfer function. So in this way we can calculate the transfer function of a given rotational mechanical system. Okay, here we use the matrix method, that is Cramer's rule. If we use Cramer's rule, then it will be very easier to understand and solve the transfer function very quickly. You can get the transfer function very fast if we use the Cramer's rule. So in Cramer's rule, you already know Cramer's rule in 12th standard or 10th standard. So you all know the Cramer's rule. Just recap the Cramer's rule before starting this type of problems. So it will be very easier for you to solve this type of problem. Okay, so that's all for today's lecture, and in our next lecture, that is lecture 5 and lecture 6, there will be some analogous system force voltage analogy, force current analogy, and some more workout problems will be there. So thank you so much. Thanks for watching.